Hello and welcome to my talk about fracture of refill friction shear spot welds, microstructure, residual stresses, and other influencing factors. My name is Niklaas Becker. I'm working at the Helmholtz-Zentrum Herion and doing my PhD on the Leuphana University in Lüneburg, super advised by Benjamin Klusemann. Today's outline, first of all, I want to introduce the LESMAT project to you, which funds my research and also my PhD program. Afterwards, I will show you the refill friction shear spot welding process. Then we come to my motivation, results, discussion, summary, conclusion, and at the end to the outlook. LESMAT is a project from Technology Transfer Lightweight, which is sponsored by the German government, which had the approach for clima-friendly mobility due to lighter trains and ships. And therefore, we changed the design from integral to differential structure, which results in many new structural joints. While we with Helmholtz-Zentrum Herion concentrate on building on railways, since they are mostly built of aluminium. Refill friction shear welding was developed in Helmholtz-Zentrum Herion at 1999 and is a solid-state joining process, which is carried out by a three-part coaxial tool, which contains the shoulder, the probe, and the clamping ring. At the bottom, you see the welding process in 4 steps. Before the actual weld starts, the weld object is getting clamped by applying a clamping force. And afterwards, the probe and the shoulder start to rotate. While in this case, the shoulder plunges into the material, the pin accommodates the displaced material. And the refilling stage, it's in the opposite. So the pin pushes the material back while the shoulder gets pulled out of the material. At the end, the clamping force is taken away, and then so the process ended with that step. The major advantages of the process is that it is compared to metal arc welding. It's an environmentally friendly process. It's applicable for high-strength aluminum alloys and is seen as a potential successor for resistant spot welding and riveting and aerospace and automotive industry. Refill friction shear spot welding results in a typical microstructure, as you see here, where we have the steer zone in the middle of the spot weld, where we have complete dynamic recrystallization. Next to the steer zone, there comes the thermomechanically affected zone, where we have strong elongated grains, but no complete recrystallization. And next to the thermomechanically affected zone, we have the heat affected zone, where we don't have any mechanical influence anymore, but still thermal influences, which results in grain grossing. The feature frequently named in literature are the bonding ligament, which is an oxide layer, which remains between the sheets, as you see in the picture. A drop region, which is caused by the circular material flow, and a hook, which is an instinct defect in refill friction shear spot welding and is known as potentially strength relevant. Since refill friction shear spot weld is supposed to deal with aerospace and automotive industry, we have to ensure that we have good fatigue, high cycle fatigue strengths, and therefore there is also some literature about it with different approaches. But it's used to be that they do, like Large did it, quasi-static process optimization for here 6000 series, and then took those welding parameters for fatigue testing, and they were able to reach only 9% of quasi-static shear strength. Everest did some similar investigations for 7000 alloy, reaching 10% of the quasi-static shear strength. So basically, the approach to do a quasi-static optimization and try to improve the fatigue life is not working very well. So I tried to go for a different approach, as I've shown myself, that it was able to deflect fatigue cracks with the help of residual stresses. And there's also different literature about that. For example, Projet observed the influence of microstructure and residual stresses in friction shear welds and came to the conclusion that the residual stresses outweighs the influence of the microstructure. And Ma et al. Also investigated the fatigue cracks in friction shear welds and even had problem to initiate fatigue cracks in compression loaded areas. So my first first approach was to influence the stress distribution, residual stress distribution due to influencing the welding parameters, as you see on the left-hand side. Here we changed the plunging time, so also total, the welding time, but only saw that we could affect the range of the residual stress affected area, but not the absolute height of the weld affected, so residual stress affected area. So we came with a different approach, which you see here on the right-hand side, where we influence the residual stress profile due to simultaneous hot working. That was done, and so where we milled a pocket basically in the lower sheet, and due to the applied clamping force, the upper sheet gets deformed in the lower sheet. This basically results in the microstructure you see on the left-hand side, where we see on top the reference specimen, where we basically have no defects in the weld, and the steer zone, thermomechanically affected zone, and heat affected zone, as mentioned before. Below we see the resulting microstructure from the modified sample, where we see that we have defects, like here we have voids, and also we have a lack of refill. To avoid these lack of refill, especially for CT specimens, we did some underfill configuration to just avoid those defects. And below you see the hook configuration, while this is the hook configuration of the upper, so of the reference specimen. This is which is actually the best hook configuration, is a flat one, but because it's initiated as a crack nucleation. And so the crack doesn't appear to go to the upper or to the lower sheet. While we see in E, which is with the lack of refill, we actually don't have a right hook configuration, since we have voids in the area where the hook is supposed to be. And with F, we see the hook configuration of the sample with a modified sample with underfill of 0.2 millimeters, where we have an upbending hook, which is not particularly good for fatigue results. Afterwards, we did some hardness measurements to see if we could influence the hardness due to the hot forming process. But basically, we saw that the hardness distribution in the reference specimens, which we see up here, is pretty much the same as in the lower one, except that we have a slightly bigger heat affected zone in the modified specimen, which is also not very good. The white areas you see here are corresponding to the areas where the pocket is, where we just could not measure any hardness since there's no material available. So summarized, we have in the modified specimen, we have volumetric defects such as lack of refill, voids, and underfill. We have an unfavorable hook formation, and we have no significant changes or no significant improvement in hardness corresponding strength. But what we saw, that we increased the fatigue life significant. On the left-hand side, you see the fatigue curve of a lab shear sample, where this is the Euler curve of the reference specimen, and this is the Euler curve of the modified specimen, where we're able to increase the number of cycles for a maximum load of 3,000 Newton from 250,000 up to 10 million, while the endurance limit for the reference specimen was 930 Newton, and in a modified sample, almost 3,000 Newton. In the cross-tension configuration, it's the same. So we saw the reference specimen is again the black dots, while the modified specimen are the gray ones. Here you see also the ones with the lack of refill. This is why we decided to set the underfill of 0.2 millimeters just to fill it, because then we were able to even further improve the fatigue life. We haven't done that for lab shear because it was not necessary. The results were still very good, but I come to that later. And here we saw, especially with lower loads like 800 Newton, we were able to increase the number of cycles from 850,000 up to 10 million, while the endurance limit of the reference specimen was 125 Newton, and with the modified sample is up to 800 Newton. Yeah, this is the fracture which results from the different configurations. On the left-hand side, you see reference lab shear sample where the crack initiates where we would expect it, like in between the steer and the thermomechanically affected zone, and then propagate horizontal through the sample. While in lab shear, we see that the crack does not appear in the area of the spot weld, but in the base material. So this is also the reason why we haven't done the underfill step for lab shear, because we didn't see the crack appearing close to the spot weld. Below you see the cross-tension samples, while this one is the one without the 0.2 millimeter underfill, where we have a classic pull-out of the spot weld. And this is the one where we have the underfill, where the crack propagates along the heat-affected zone. So we had a closer look and did some EBSD measurements in 3 positions in the center of the sample and 3.5 and 5.5 millimeters. While we see, this is the reference specimen, this is the modified specimen. And we see that at the center and basically at 5.5 millimeters, we have no significant changes in the grain orientation. But we saw that at 3.5 millimeters, we significantly changed the orientation of the grains. And therefore, we had a look to the pole figures of this position. This is both like in 3.5 millimeters, while this is the reference specimen and this is the modified specimen. So we see in the reference specimen, we have a shear texture, which is very pronounced. And in the modified specimen, we still see a slightly shear texture, but much less pronounced as in the reference sample before. We also saw that we have slightly smaller grains in the modified sample than in the reference sample. Yeah. Additionally, we did some residual stress measurements with X-ray diffraction and transmission. First of all, I want to say we have some residual stress profiles, which you see here. They come from the extruded hollow chamber profile where we took the samples from, but basically should not influence the fatigue properties, since the residual stresses are formed by the welding process, as you see here anyway. Again, on top we have the reference specimen where you see the typical residual stress distribution, like having a huge amount of tensile residual stresses within the spot weld and around it. While this is always in X direction, this is in Y direction. But what we see below, which is very interesting, that due to the deforming process, we have basically no or very little residual stresses within the spot weld, and which is particularly notable that in the area where the steer zone and the between the steer and the thermomechanically zone where the crack is supposed to appear, we have basically compressive residual stresses here. So, but what happened to influence the stresses? Here on the left-hand side, you see the welding process again. With the first picture before the welding process, we defined the initial lengths here, like as you see here. So when we then apply the clamping force, the upper sheet is going to be elongated, since L1 and L2 is longer than the initial lengths here. When we release the clamping force, it comes to compression, since L3 is shorter than L1 plus L2. And this results in compressive forces occurring in the spot weld due to the elastic spring brake and the length ratio, which basically compress the spot weld. So the microstructure orientation and grain size are caused by the axial force resulting from the elastic spring brake, while the residual stresses are caused by compression resulting from the elastic spring brakes and the length ratio. So let's summarize. In the lab shear sample, we have volumetric defects and geometric features, which are not very good. But they are not strength significant, because they turned out worse in the modified sample, but we still have better fatigue life. Also, the texture and the grain size have no direct influence, because we have seen the crack doesn't appear in the crystallized area, but in the base material. In the cross tension, we see the same. Basically, the volumetric defects and geometric features are unfavorable and therefore turn out worse, but still we have better fatigue lives. And also the grain size and texture have also no direct influence on the fatigue life, as the failure appear in the transition zone and not in the recrystallized area. So the residual stresses are responsible for the significant increase in fatigue life, as they not only slow down the crack propagation, but in case of lab shear samples, they were also able to prevent even the crack from nucleate. So the conclusion about it is that residual stresses are the most important factor when it comes to influencing the fatigue life of refill friction steel spot welds. by combining refill friction shear spot welding and hot forming, it was possible to influence the residual stresses, and those achieve significant increase in fatigue life. And these findings are material independent and can most likely also combined with other welding processes. Further studies should be carried out to investigate the effects such as pocket size, pocket depth, clamping force, and also the temperature. Here we come to the references, and we come to the end of my talk, and I would say thank you for your attention.